Okay, so now that we've seen how to predict the entropy changes in a system, remember the system is part of is a thing that we're studying, and it's part of the entire thing, and that entire thing is often referred to as the universe. Now, sometimes when we use that term, it may seem very daunting, but the universe itself is made up of what we're studying, which is the system. Okay, so this is what is being studied. Usually a reaction. Everything else is called the surroundings. And when we add together the system and the surroundings, what we end up with is the universe. Okay, so that's how that plays into what we're going to be looking at here. So for example, if I have a test tube, okay, with a reaction happening inside of it, like here, okay, that thing in the test tube here, let's say this is on a bench, okay, what we're studying in the inside, that is our system. That's the reaction happening. Everything else, the test tube is the surroundings, part of the surroundings. The bench top is part of the surroundings. The air is part of the surroundings. The room is part of the surroundings. The building, the city, the state, the whatever. Everything else other than the system is the surrounding. You sum together the system and the surroundings, we end up with the universe. So when we want to predict the spontaneity of a process, we can't just look at the entropy of the system. We can use that as a starting point. We actually have to consider the entropy changes in both the system and the surroundings. So for example, if we have an ice cube, we know that at 25 degrees Celsius, that ice cube will spontaneously melt. So if we look at the system itself, which is the ice, right, because it's going to melt, it's going to go from a solid to a liquid. We know that the entropy is going to increase, so that's a positive delta S. Well, what's happening now with the surroundings? Well, everything else, right? So everything around the ice that we're studying is actually going to have the opposite change in entropy. It's going to have a negative change in entropy, meaning that there's a decrease in the entropy of the surroundings. Yet, we know that this system is spontaneous. So that means then that whatever this delta S here for the system, which is positive, is actually outweighing whatever that decrease in entropy is for the surroundings. And as a result, overall, delta S here is a positive value. Similarly, we know that a cup of hot water spontaneously cools to room temp. Well, what's happening in terms of the hot water? Well, it is cooling down. So the particles are losing energy, right? They're decreasing the number of microstates. As a result of delta S, the change in entropy there is negative, right? There's a decrease in entropy for the water, for the hot water. However, the surroundings, there's an increase in entropy. So now we have the opposite happening compared to what we saw up here. Yet this process is also spontaneous under those conditions. And what this means is that the increase in entropy for the surroundings outweighs the decrease in entropy for the system. Overall here, the delta S is also positive because of the greater contribution of the increase in entropy for the surroundings. So the point here is that we need to consider the entropy of both the system and the surroundings when we start determining the entropy change for a process. So what we're going to see is that the change in entropy of the surroundings, because we know we can determine the change in entropy of a system, right? So we know we can determine can be calculated. What about the delta S of the surroundings, right? Everything else around it. Well, we know that the delta S of the surroundings is proportional to, that's a proportionality sign, the delta H, which is the change in enthalpy of the system. Right, we've calculated delta H's before, but it's proportional to the opposite of the delta H of the system. We also know that the delta S of the surroundings is proportional to the inverse of the temperature, absolute temperature. So if we combine these two, what we can come up with now is a new equation. The delta S of the surroundings, right, everything other than the system, is actually equal to the negative value of the delta H, the enthalpy change of the system, divided by the temperature of that system itself. So the change in entropy of the surroundings is directly proportional to the change in enthalpy of the system, and it's inversely proportional to the change in the temperature. This brings us then to the second law of thermodynamics that says that in order for a process to be spontaneous, the change in entropy of the universe, so both the system and the surroundings combined, must be positive. Okay, so delta S, change in entropy of the universe. Remember, we defined the universe at the beginning up here as the sum of the system and the surroundings. In order for a process to be spontaneous, the entropy of the universe needs to increase. That means when we add together the change in entropy of the system and the change in entropy of the surroundings, whatever we get here should be a positive value. Okay, so we can say for a spontaneous process, the change in entropy of the universe needs to be greater than 0. For a non-spontaneous process, the change in entropy needs to be less than 0. And then for a system at equilibrium, we've already talked about equilibrium now, the change in entropy of the universe needs to be equal to 0. And these are for the reactions, for example, for reactions or processes as they are written. So we're defining it as we write out the particular reaction, right? This is the sum here, this very simple equation, L delta S of the universe, sum of the delta S of the system plus the surroundings. That is simply the second law of thermodynamics. In order for a process to be spontaneous, the delta S of the universe needs to be positive. So let's take a look at an example. We'll do one of these here. So it says, determine if each of the following is spontaneous, non-spontaneous, or equilibrium at the specified temperature. These are all at, oh, I'm sorry, we have, let's do A. So we have H2 gas plus I2 gas to produce 2HI gas at 0 degrees Celsius. Okay, so what we're going to do here, in order to determine whether it's spontaneous, non-spontaneous, or equilibrium, we need to find delta S of the universe. Okay, and delta S of the universe, we'll abbreviate this as UNIV, is delta S of the surroundings, or of the system, plus delta S of the surroundings. Okay, so we'll calculate each of these. We've determined delta S of the system, which is the reaction. Before, it's the sum entropy of the product minus the entropy of the reactants. So we can look these up. In our table. So we can look up these values in our tables. So the products here, we have our HI and we have our stoichiometry there is 2. Okay, so we're going to have So we can look up these values in our table in the appendix. So we have 2 times the delta S of the HI. HI is 206.3 times 2 for the stoichiometry minus the H2 delta S standard molar entropy. So 131 for I2, it is 260.57. Put the parentheses in the right place. So we sum those together, or we subtract them, I'm sorry, we end up at 21.03 for the delta S of the reaction. Remember, the reaction is the system, so that's our system here. We also now need to calculate delta H. So remember now, delta S of the surroundings, okay, is equal to negative delta H of the system, which in the system is a reaction divided by the temperature. So we need to calculate delta H of the system. Okay, so again, we can use our values from the appendix. So we have 2 times the delta H of formation of the HI. Again, that's your product here minus the delta H of the reactant. So we have now delta H of formation of the H2 plus the delta H formation of I2. We can look these up in our appendix. So we'll look up the delta H values, substitute them in. So we have 2 times delta H of formation there is 25.9. And this is kilojoules per mole minus the sum of those two. For H2, it is 0. And then for I2, it is 62.25. And that's kilojoules per mole. So you substitute that in. Let's see, that's 50 minus, that'll give you negative 10.5 kilojoules per mole. So that then gets divided. So our delta S of the surroundings would be what we just found. So negative 10.5 kilojoules per mole divided by the temperature, which is 0 Celsius, which is 273 Kelvin. Okay, so we end up there with we get 0.0385 kilojoules per mole Kelvin. We want to convert that to joules because we have joules in the one above. So 1, 2, that's 38.5 joules per mole Kelvin. So now we have both of the things that we need to calculate the delta H. I'm sorry, the delta S of the universe. So delta S now of the universe, delta S of the system, plus delta S of the surroundings. Okay, we have the surroundings. We have the system. So there's negative 10.5. I'm sorry, that's not the negative 10. That's the delta H. Delta S of the system we found above, which was 21.03. Joules per Kelvin mole, plus delta S of the surroundings. We just found this as 38.5 joules per Kelvin mole. Obviously, this is going to give us a positive value of 59.5 joules per Kelvin mole. So that's a delta S of the universe. Okay, that's what we're trying to find. This is a positive value. Okay, so then that will tell us then that this process is spontaneous as written. Okay, and that as written is the actual reaction that we studied up here, H2 plus I2 to produce HI. So you need to go through, if you're using that equation, right, we need to go through and find not just the delta S of the system, where we can look up the delta S standard entropy values in the table, but we also need to calculate delta S of the surroundings, where we're using the delta H of the system. Again, delta H values we can find in the appendix, substitute it in, don't forget to incorporate the temperature, solve for delta S of the surroundings, and then just sum those together to get the delta S of the universe. So we've seen the second law of thermodynamics that says the change in entropy of the universe needs to be positive in order for our process to be spontaneous. The third law of thermodynamics says that the entropy of a perfect crystalline substance is zero at absolute zero. So what does that actually mean? Well, we know entropy S is equal to K, Boltzmann constant, times the natural log of the number of microstates. So if you think about what happens at absolute zero. So at absolute zero, right, which is 0 Kelvin, okay, all motion stops. So nothing is moving. So even the particles in a crystal or in a solid, which is what will happen when you cool anything down to not a solution, a solid. If you cool anything down to absolute zero, all the motion stops. They stop moving. They get closer and closer together. All the particles in a solid, they will occupy a fixed position, meaning there's only one possible arrangement. Because they cannot move. They're locked in position. So what this means then is our W is equal to 1. So if I substitute that into my equation, S equals Boltzmann constant times ln of 1. Well, what is ln of 1? Well, this here is equal to 0. What is 0 times K? 0 times K is equal to 0. So this is the derivation of the third law of thermodynamics. The entropy of a perfect crystalline substance at zero is zero, at absolute zero. As temperature increases from absolute zero, you are giving the particles more energy, and they will then start to occupy more microstates. There will become more possible arrangements for those particles as the temperature increases. And as a result, as temperature goes up from the absolute zero down here, we will see the entropy increases as a result. All right, so that's the third law of thermodynamics.